Section B, Proving Triangles Congruent.
What do we mean by congruent triangles? Well, we say that two triangles are congruent if and only if their corresponding parts are congruent. This is a very powerful statement. Let's see what it means.
Here are two congruent triangles. To precisely state their congruence, we say triangle ABC is congruent to triangle DEF. We can't say triangle ABC is congruent to triangle FED. Why? Well, let's see why.
By saying that triangle ABC is congruent to triangle DEF, we're saying that corresponding angles and sides are congruent. So, angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent to angle F. Segment AB is congruent to segment DE. Segment BC is congruent to segment EF. And segment AC is congruent to segment DF. If we were to say that triangle ABC is congruent to triangle FED, we'd also be saying that angle A is congruent to angle F, which is wrong. Notice how we show what parts are congruent in the diagram? We mark them with little lines to show which ones match up.
Note that the definition, two triangles are congruent if and only if their corresponding parts are congruent, uses the phrase if and only if, reminding us that this statement is really two statements, the statement itself and its converse.
Our statement is, if two triangles are congruent, all of their corresponding parts are congruent. This statement will be very useful to us later on when we work out more proofs. In fact, we'll refer to this definition so much it's often given nicknames like the definition of congruence, fuzzy face, and CPCTC, which stands for corresponding parts of congruent triangles are congruent.
The converse is, if two triangles have congruent corresponding parts, then the two triangles are congruent. Because this statement requires us to find 6 matching pairs of items, all 3 pairs of sides, and all 3 pairs of angles, before we can claim that two triangles are congruent, it takes a lot more time than our first statement. We don't really need all of that stuff to prove that two triangles are congruent. Just wait, you'll see.
So let's do a few experiments to try to come up with 3 different postulates to use in our triangle proofs.
First, try this. Put your fingertips together like this. Now, bend the middle fingers together so the first knuckles are touching. Now, try to take your ring fingers apart without moving your other fingers. You won't be able to.
Try this. Take 2 drinking straws. Cut the first one into 3 pieces, one 4 inches, one 3 inches, one 2 inches. Do the same with the second straw so that you have 2 identical sets of 3 pieces. Make a triangle out of each set. Try to make the triangles look different. You won't be able to. If 2 triangles have the same side lengths, they will always be the exact same shape.
This is a key postulate in geometry, the side-side-side, or SSS postulate. So we don't need to match all 6 pairs of sides and angles. It's enough to just match the 3 sides to prove that the 2 triangles are congruent.
Side, side, side postulate.
Side, side, side postulate. If 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. The side, side, side postulate.
Let's try an example where we can put the side, side, side postulate to good use. This isn't a theorem we're proving, just a specific problem that you might find on a test. We'll use a proof table to work it out.
Given triangle QRS, with M as the midpoint of RS and QR congruent to QS, prove that triangle QRM is congruent to triangle QSM.
Note that we are not given the information that QM is the bisector of angle Q.
Let's set up our proof table. Our first step is to put down all of our given information. M is the midpoint of Rx, and segments QR and QS are congruent.
Our second step is to state that segments RM and MS are congruent. That's the definition of a midpoint.
So, now we've got 2 pairs of sides congruent. The pair we're given, QR and QS, and the 2 that are divided by the midpoint, RM and MS. The only side left is QM, which is easy to prove. Because it's shared by both triangles, we just state that QM is congruent to itself by using the reflexive property.
Now that we've got all 3 sides congruent, we can state our goal. Triangle QRM is congruent to triangle QSM. thanks to the side-side-side postulate.
Pretty simple, huh? We've just used the side-side-side postulate to prove that two triangles are congruent. Now, let's take a look at the side-angle-side postulate.
We'll start with another experiment. Get a friend, 2 rulers, 2 protractors, 2 sheets of paper, a baseball, a glove, and a bat.
Pick 2 side lengths and 1 angle measure. Let's say the sides measure 4 inches and 7 inches, and the angle is 82 degrees. Now both of you draw triangles which have a 4-inch side, a 7-inch side, and an angle of 82 degrees between them. Your triangles should look the same. This illustrates another important postulate of geometry, the side-angle-side, or SAS postulate. Good job. Now go play baseball.
The side-angle-side postulate.
The side-angle-side postulate. If 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, then the triangles are congruent. The side-angle-side postulate.
Here we have 2 triangles that resemble the last pair. In fact, they went to high school together and ran in the same social circles. We'll use the side-angle-side postulate to prove they're congruent. What we need to do is prove that they have 2 congruent corresponding sides and 1 congruent angle in between. Given that AB is congruent to BC and BD is congruent to BE, we'll show that triangles BAD and BCE are congruent.
Let's get started by stating our given information. Segment AB is congruent to segment BC, and segment BD is congruent to segment BE.
So, we have been given 2 pairs of sides. To use the side-angle-side postulate, all we need to prove is that the angles between the sides, angle 1 and angle 2, are congruent. And we notice that angle 1 and angle 2 are vertical angles. Remember the definition of vertical angles? Vertical angles occur opposite each other when 2 lines intersect. And vertical angles are congruent. So, we can state that angle 1 is congruent to angle 2 because of the definition of vertical angles.
So, for triangles BAD and BCE, we have 2 sides and their included angles. We complete our proof by stating that triangle BAD is congruent to triangle BCE. Our reason is the side-angle-side, or SAS postulate. We're done!
Let's try one last experiment. With a friend of yours, agree on 2 angle measurements. Remember, they can't both be 90 degrees or greater, and 1 side length. Now draw a triangle starting with an agreed-upon side length and putting the agreed-upon angles at each end of the side. Say that you start with a 36-inch side. Put a 40-degree angle on one end and a 60-degree angle on the other. Now complete the triangles. Once again, your triangles should look identical. We have illustrated the following important postulate of geometry, the angle-side-angle, or ASA postulate.
Angle-side-angle postulate.
Angle-side-angle postulate. If 2 angles and the included side of one triangle are congruent to 2 corresponding angles and the included side of another triangle, then the triangles are congruent. The angle-side-angle postulate.
Let's look at the triangles here, ABC and EDC. Let's prove them congruent. Sound good? Great! Let's state our given information. We're given that AB and DE are parallel to one another and their lengths are congruent. We want to prove the triangles are congruent using the angle-side-angle postulate.
Let's get started by stating our given information. Lines AB and DE are parallel, and AB and DE are congruent.
Remember the alternate interior angles theorem? Lines are parallel if and only if alternate interior angles are congruent. Well, we'll use it for our reason in step 2. It lets us state that angles A and E and angles B and D are congruent to each other.
So, for each triangle we have a corresponding side, and 2 angles at its ends. By using the angle-side-angle postulate, we can set triangle ABC congruent to triangle EDC. Our goal is accomplished.
Now that we have some ways to prove congruent triangles, let's move on to using